Hello, we will introduce CDEFG, a dataset for continuous dynamic ego-centric fine-grained gesture recognition. Hand gesture recognition is a computer vision task focusing on giving computers the ability to recognize gestures. The field of hand gesture recognition is extendable to various fields, including mixed reality headsets, virtual reality, and more. As such, there is a need for quality hand gesture dataset to train models on. However, there are a few issues with currently existing hand gesture datasets. Firstly, most existing datasets are captured against the same background, reducing their ability to generalize to diverse environments. They also contain a limited number of gesture classes. Most datasets are also non-continuous, recording only isolated gestures. Even then, some continuous datasets often include transition frames that makes it obvious when a gesture starts and ends.
Here's our main contribution, the CDEFG dataset. CDEFG stands for Continuous Dynamic Ego-centric Fine-Grained Gesture Dataset. It contains 164 subjects and 105 gesture classes. To increase scene diversity, we perform background swapping on videos. After harmonization, our dataset expands from 32,000 raw videos to 97,000 swapped videos. We evaluate the dataset on both skeleton-based and RGB-based gesture recognition models and show consistent improvements. The example below shows the screenshots from our generated dataset videos.
This figure shows the overall data pipeline, which starts from data collection. From this, we can extract the skeleton information as well as performing background swapping on the videos to increase background diversity. Tinted glasses were used to record the subjects as they perform all 105 gestures twice. Each recording session captured 5 randomly selected gestures, performed continuously in a single video. We will split the gestures into individual gesture clips using manually annotated label files. There are a total of 5 pairs of numbers, denoting the start and end of the gesture. Using the labels, the continuous gesture videos are split into single gesture videos and converted into frames. Skeleton data is extracted by passing the RGB videos through the Wheeler model, which then detects hands, estimates joints locations in 3D space, and reconstructs them. These estimated joint positions serve as our skeleton data.
After collecting raw videos, we use a segmentation model to extract the hand mask for every frame. This gives us a clean hand-only region that can be composited onto new backgrounds later. And then we choose replacement backgrounds that fall under 3 types of backgrounds: daytime outdoor, indoor scene, and night outdoor scenes. This increases visual diversity across diverse backgrounds. Finally, we fit the raw videos, the generated hand mask, and the selected new background into a harmonization module, which produces realistic and visually consistent final videos.
We will then take our segmented isolated gesture dataset and evaluate its performance across a range of single gesture, RGB-based, and skeleton-based gesture recognition model, focusing on its accuracy, flops, and parameter counts. For skeleton-based models, our experiments show that TDGCN has the highest accuracy, and that all the models exhibit strong performance, with all of them having an accuracy above 93%. It's also interesting to note the Yates GR model, which has a relatively high accuracy of 95% despite having the lowest flops. For RGB-based methods, we find that the NAS model has the highest accuracy with 90.93%, while MobileNet V2 has the lowest flops value with 0.31. The best model for accuracy and computational trade-off is the DSM model, which has an accuracy that's just 2% off from the best model despite having the second smallest flops value. Our experiment also showed that skeleton-based methods have a higher accuracy than RGB-based methods. This is due to the fact that skeleton-based methods are not affected by the background features. Regardless, our experiments show that our dataset can be used as a benchmark for training and testing single gesture models.
This table shows the impact of final data on model performance. When models are trained on only raw videos, accuracy drops sharply when testing on unseen background types. However, when trained on final data, the combination of raw and harmonized videos, all models become much more robust, especially motion RGB and ActionNet. This proves that background diverse training data significantly improves generalization.
In conclusion, we created the CDEFG dataset, a continuous large-scale multimodal dataset with 164 subjects and 105 classes. This dataset will then be augmented through background swapping and harmonization, and can be split into a single gesture dataset. We will then evaluate this dataset on various RGB and skeleton-based models. The experiment results show our dataset can be used as a benchmark for such models. Furthermore, in experiments done by our colleagues, continuous gesture model performs poorly on this dataset. This shows that there is potential for our dataset to be used as a benchmark to improve current continuous hand gesture recognition models.